The objective of this video is to establish the design sizing approach for induction machines. And we're going to build off of the key results that I've already got summarized on the screen. So starting on the left, we've got our cross-section of an induction motor labeled as we've been labeling it with a rotor angle referenced to the horizontal axis via slot 1. On the right, we are assuming that we have an air gap field of B delta, and that when we have this air gap field, it causes a rotor bar voltage, as given by this phasor expression, which causes a rotor bar current, given by this expression, that depends on our rotor impedance. And we've got this all critical angle of zeta r, which is the angle of our rotor impedance. And from this expression, we can then calculate the actual current within an individual rotor bar, where alpha I superscript r is the location of the rotor slot in the rotor reference frame. That is, it's referenced to slot 1. So when we have this situation that we've described up here, we end up finding that we have 3 resulting current linkage waves that rotate in the air gap of our machine. And we've derived these waves in a previous video, and so I'm summarizing them here again. We've got a current linkage wave created by the currents in our rotor. We've got a current linkage wave created by the magnetizing currents in our stator. And we've got a current linkage wave created by our stator currents that are reacting to our rotor. That is, this current linkage wave is created by our rotor current referred to the stator. And so for each of these, I've written an expression for what the magnitude of the wave is. On the case on the left, we've got it in terms of our rotor quantities. For our magnetizing current, we've expressed it based on our stator winding design and our magnetizing current component in the stator currents. For our rotor current referred to the stator, we've got a reference to our stator winding design and the magnitude of the rotor current referred to the stator. And so each of these current linkages can be modeled as having been created by an equivalent linear current density that is either acting on the outer bore of our rotor or the inner bore of our stator. And we've already derived the expression for the current linkage, or the equivalent current density acting on the outer bore of our rotor, as shown on here. And we can easily follow that same step to do it for the linear current density acting on the inner bore of our stator. And I've color-coded all of these because now what we're going to do is plot these linear current densities on a cross-section of our machine and show how this relates to our machine sizing equations. And so here we've got our quantities plotted on the cross-section of our machine. Starting with the rotor linear current density, we can see that we've got this plotted on the outer bore of our rotor in a manner that we've been plotting in the past. So this portion of the diagram matches your previous lecture video. Then moving radially outwards, we've got our magnetizing field of the machine. And we can point out that the magnetizing field of the machine is rotating counterclockwise at omega t, whereas the current density on the inner bore of our rotor is rotating counterclockwise and is located at an angle of omega t minus zeta r. So we've got this linear current density on our rotor lagging the magnetizing field of the machine by zeta r. Next, moving outwards, we have plotted the linear current density that our stator produces in reaction to the rotor's field. And so we've got that plotted up here. And you can see that this is just the opposite of the linear current density that is on our rotor. So where our rotor current density peaks coming out of the page, the stator current density peaks going into the page. And so it's got the same angles as we had indicated for our linear current density on the rotor. And following the convention of the AC machine sizing unit from the other month, well, we can label a zeta r prime, which is the distance from the peak of our stator linear current density, the peak of our stator linear current density due to the rotor fields, coming out of the page from the axis of our magnetizing field. And so that's this angle that we've plotted up here. And so you can compare this in your notes to what we had in the original AC machine design sizing equations. And we can also define this angle phi RI, which is the separation between the axis of our of this current density and our magnetic field. So all this is set up to match the AC machine design sizing video. Moving further radially outward, we have our third current density, which is the magnetizing current density. So this current density has to be aligned with a magnetizing field, so it's going to have an axis that corresponds to the magnetizing field. So you can see that there's zero current here, and then when we start going this way, we have current coming out of the page, but if we go this way, we've got current going into the page. And it's going to peak in the region, the interpolar region between the magnets at our quadrature axis. So with all these current densities plotted, with our three sets of current densities plotted, we can talk about torque on the rotor. And in a previous video, we calculated torque on the rotor due to the rotor linear current density and the magnetizing field. And so we can summarize that result now. And we had this expression here, which was that our torque is equal to 2 times the volume of our rotor times our average shear stress. And this is a very familiar quantity to us at this point. That's what we have always found out when we're doing our machine sizing equations. And we found that the average of our shear stress was equal to our magnetic loading times our rotor's electric loading divided by 2, and then times the sine of this angle, zeta r, our rotor impedance, plus pi by 2. And I'm noting here that is simply equal to the cosine of zeta r. So that was a result we had, and we commented that it wasn't especially useful for machine sizing because we don't usually like to think about sizing a machine in terms of the rotor's electric loading. We'd prefer to talk about it in terms of the stator's electric loading. Now I'm going to show how I'm going to summarize the results from how we calculated machine torque from our original AC machine sizing unit, which would be that in this case, it would correspond to us considering this current linkage here, the blue current linkage, with, the blue linear current density with our rotors, with the air gap magnetizing field. And so in the AC machine design sizing unit, we had a magnetizing field created by the rotor, and then we just looked at the stator's linear current density. And in this case, we're looking at the stator's linear current density, but we're only looking at the portion that's associated with reacting to the rotor fields, and we are letting the current density that's associated with creating the magnetizing fields, we're leaving that alone because we established in that previous video that any current that's aligned with our magnets will create no torque. Right? This current linkage, this linear current density that we've drawn in green, is aligned with our magnets in a way that it can create no torque, and we proved that in our AC machine design sizing video. So therefore, we can see that the only current density that is capable of producing torque on our stator is the blue current density, whereas the green current density is just required to establish the magnetizing field. And you can see that when we've done this, we end up getting the exact same expression for our shear stress in the air gap of our machine. So we end up getting the same expression for torque if we study the machine as having this blue linear current density reacting or interacting with this magnetizing field, as we get when we consider the rotor as having this brown linear current density interacting with the same magnetizing field. So this is satisfying. This shows us that our laws of physics are being followed. We can study the stator current densities alone and end up getting the correct torque on our machine, or we could study the rotor current density with the magnetizing field and also get the same torque on our machine. So this is good. It helps us to understand the physics of what's going on in our machine, but yet still it is not that useful from a sizing perspective because this quantity right here, AR hat, is still the linear current density on our rotor, or we could say it's the linear current density on our stator that's reacting to our rotor, but it is not the electric loading of our stator. And so, yet again, it still is not entirely helpful for sizing the induction motor. And to get to a point that we can talk about sizing the induction motor, we need to take a step further and acknowledge that in reality, there's actually only one linear current density in the stator, and it's the combination of our magnetizing linear current density and the current density that's reacting to the rotor. And so when we combine the two stator winding components, we've got our magnetizing field and our rotor current referred to the stator. We can do this in the phasor domain, and so we've already established that the magnetizing field, we'll treat this as having an angle of 0 degrees, and the rotor current referred to the stator is always going to be at an angle of pi by 2 minus zeta r relative to our magnetizing field. So it's always rotating the counterclockwise direction by this angle relative to our stator field. And so we can talk about this giving us a final phase u current of I u hat e to the j phi I, where phi I is the angle that results when you sum up these two components. So if you take this, you can then bring this back to the time domain and get an expression for your phase u current like this, which will produce a current linkage of this form and a linear current density of this form. And finally, the peak of this linear current density here is the electric loading of our machine. And to help this hit home, I'm going to show on the screen our AC machine design sizing notes at the same time. So we've established that we want to have currents of this form, and you can see that in our AC machine design sizing unit, we said that, hey, if we have three-phase currents that have alpha W as their angle and then are varied by 2 pi by 3, we will end up getting a current linkage of this form over here where we've got an angle of alpha W. That is, our current linkage is at an angle of alpha W. And so that corresponds over here to this expression. And in the AC machine design sizing unit, we established that this angle alpha W should be of the form omega t plus phi I. Well, that is exactly what we have just decided in our induction motor unit, right? We've got an omega t plus phi I for this alpha W. And this set of currents is resulting in this current linkage and this linear current density. And so you can see that matches up here precisely with what we just said in our notes. Now, furthermore, going over to the AC machine design sizing video, we drew this cross section of our machine at that point, and we had our magnetizing field located at theta equals omega t from horizontal, and then it had this angle phi I, which was the same angle that we had in our currents. So that phi I is the phi I up here, and this phi I is now appearing in our new notes as well. So this phi I that we see in this diagram does correspond to the angle of our stator currents that results when we combine our magnetizing component with our reaction to the rotor. We're now going to draw this out to make it crystal clear, but I want to highlight that all this material is building off of what we already set up back when we covered the AC machine design sizing. So you'll see I've now sketched a cross-section of our machine with these updated linear current densities, and I've done away with the stator having two linear current densities, and now it just has a single linear current density, which is this expression right here. I've still got our rotor linear current density drawn, and then of course I've got the magnetizing fields in the air gap of the machine. And the angles on here, well, we've got the location of our rotor linear current density at the same location as always been relative to our magnetizing field. And now we've got phi I, which is the separation between the axes of our stator linear current density and our magnetizing field. And that phi I directly matches the phi I that we had in our AC machine design sizing video. So you can see this phi I right here matches this phi I up here. And zeta of the stator current is the separation between our magnetizing field and the peak linear current density coming out of the page, and that also directly matches what we've drawn in this video over here. And now we can directly use the results of our AC machine design sizing video to write out our sizing law. And so we get our torque expression here. And you can see this is exactly the same as we had in our AC machine design sizing video. And this cosine of zeta term, so zeta is now this angle. It's not our rotor angle, but it's not the angle of our rotor impedance. It's the separation between our stator linear current density and our magnetizing field. Your textbook says that for an induction motor, this cosine of zeta will typically be approximately 0.8. It just gives you a line in the sand to say, hey, this is approximately what this angle is going to be. So you can start thinking about this in terms of sizing your machine. You could pick a linear current density and a magnetic current density and then know how much torque you're getting based on the volume of your rotor by assuming that the cosine of zeta is approximately 0.8. Now we're at a point that we can summarize how to size an induction motor. And when it comes to sizing the induction motor, it's important to note that our electric loading and our magnetic loading are not actually independent. Because remember, your stator current is what's establishing your magnetic field. Your stator current establishes your magnetic loading. So my recommendation is that you don't actually pick distinct values of A hat and B delta. So in sizing synchronous machines, we would say, hey, we're going to have an electric loading of 50 kiloamperes per meter, and we're going to have a magnetic loading of 0.7 Tesla, and boom, we'll use these equations to figure out the volume of our rotor and so on. But in an induction motor, it's wise to acknowledge that these are not independent quantities. And so instead, I recommend that you pick a reasonable value of the shear stress in your air gap from table 6.4. And then you pick a reasonable value for B delta, and from there you solve for the volume of your rotor. In principle, we've talked through how to size an induction motor. However, there's one more important thing that I want to address, and that is how power factor relates to all of this. And so let's go ahead and discuss that, and let's discuss it in the context of a case where under rated conditions, our rotor impedance angle is 0. That is, our rotor appears nearly perfectly resistive under rated conditions. And for a lot of machines, this is a reasonable approximation because at rated speed, your slip is fairly small. Maybe it's 1%, maybe it's 4%, but it's a pretty small value. And for this case, I've drawn our phasors over here. So when zeta r equals 0, if you recall up top, we have our rotor current referred to the stator phasor as occurring at pi by 2, an angle of pi by 2, or an angle of 90 degrees counterclockwise for our magnetizing current, because this term simply drops off. And so phi is the angle of our final stator current relative to the magnetizing current. And we can see that in this case, we've got our magnetizing current on the horizontal axis. Our rotor current referred to the stator is rotated 90 degrees, so it's going upwards. And we sum these two components to get our total stator current phasor. And so this is at an angle phi. And before we even talk about power factor, we can just go back to this simple guideline that our textbook gave and relate our two current components to our overall stator current magnitude. And this gives us a guideline here that in a typical induction machine, we expect that under rated currents, about 80% of the magnitude of our stator phase current is going to be used to create torque, right? That is the current component that we see in the air gap here. This blue current component we see up here, which creates torque. And if zeta r equals 0, it's used in a maximum torque per ampere type of mode. And then we can see that 60% of our current magnitude is used to magnetize the machine. And this component, it really doesn't matter how much torque is being created or what your operating point is. Your magnetizing current is directly related to the voltage that you're applying to your stator. So this current component is always there regardless of if you're making torque or not, whereas this current component will fluctuate based on how much torque you're making, and it will peak at a value of about 80% of the stator phase current. So this is, again, very hand wavy, since we had to rely on this observation up here, this empirical observation that typically the cosine of zeta is 0.8. But it gives us a design point, or it gives us a data point for if we've created a good induction machine or not, or if we're seeing typical values or not when we talk about current ratings of the machine and how the current distributes itself. But that's not really our end goal here. Our end goal is to talk about power factor. And so let's consider a simplified equivalent circuit of our induction machine. And to talk about power factor, we're going to further make a simplification by assuming that Rs and Ls sigma are negligible. They're so small compared to the rest of our circuit that they don't matter. That's a very, again, hand-wavy approximation. And the reason that we're doing that is because we want to relate power factor of the machine to our rotor current referred to the stator. We want to end up figuring out, hey, if I know that my power factor of the machine has a certain value, how do I expect my magnetizing current and my rotor current to distribute themselves for the total terminal current going into my machine? And the second question is, can I somehow use this to get the actual rotor current in the bars of the machine? And so the reason that comes up is that power factor is defined as the angle between our stator terminal current and the voltage that's applied out here. Well, if we assume that this branch right here has no impedance, then the voltage that's applied out here is simply our back EMF, and it's a much more simple system to analyze. And so our equivalent circuit then becomes this simple circuit over here. And we can draw our phasor diagram for this again. And now we can comment that our power factor is calculated as I described earlier. And so when we do our calculations here, we see that we finally are able to relate our actual rotor bar current, the physical current that's flowing in our rotor bars, to the power factor of our machine, to that turns ratio that we introduced in our previous video, the turns ratio that we introduced in the video on the equivalent circuit of an induction motor, and the rating of our stator current. So this expression that we've derived here, again, remember it's an approximation. It has a few sources of error. One thing, it depends on us having our rotor impedance have an angle of 0. And it depends on assuming that the stator's leakage inductance and resistance is negligible compared to the rest of the circuit. So when we have these assumptions, we're able to make these assumptions, then we're able to finally calculate the actual rotor bar current in terms of the power factor of the machine and the rating of our stator currents. And so this is an important design relationship. We're going to use it when we talk about the analytic design of induction machines, because it gives us a means to size our rotor bars. Just like we need to figure out what size of wire gauge we should use based on our current density and our rating of our stator terminal current, we can now figure out what kind of slot size and bar size we need to achieve a desired rotor bar current rating. And in order to figure that out, we need to know what the rotor bar current rating is, which is what this expression tells us how to do. Okay, that concludes this video. In this video, we've established a design sizing approach for induction motors, and we did it based off of the first principles of physics that we've been developing for how an induction motor works. We identified distinct portions of equivalent linear current density in our air gap of our machine. We've got a rotor linear current density, and then we've got two components of stator linear current density. One component associated with magnetizing our machine, and a second component associated with creating torque on our machine, or reacting to what's happening on the rotor. And we use this to get ourselves back to our comfortable AC machine design sizing law. That's in terms of the stator electric loading, the magnetic loading of the machine, and the angle between these two waves in the air gap of our machine. We noted a basic design rule of thumb for how a well-designed induction machine may perform. And then we summarize the design sizing steps and use this, along with some assumptions, to establish a design equation for the required current rating of our rotor bars relative to the current rating of our stator winding.